Hello, my name is Andreas Ramranota, and I will be explaining about the materials and equipment used in this practicum, the work process, and the conclusions of this practicum.
Hello, my name is Nicholas Kevin Jonathan, and I will be explaining about the objectives, literature review, results and analysis, and the discussion. First off is the objectives. There are two main objectives in the practicum. Firstly is to determine the equilibrium constant of a solute into immiscible solvents. Secondly is to determine the degree of dissociation of solute in the two solvents. So next up is the literature review. First is about miscibility and density. Miscibility is defined as the property of two substances to mix in all proportions. It can be classified as fully miscible, partially miscible, or completely immiscible. When two immiscible liquids are mixed, they will form two different layers, top and bottom, with the top layer being the lighter liquid and the bottom layer being the heavier liquid. When a solid that is soluble in two different and immiscible solvents is mixed together, there will be a state of equilibrium between the concentration of solute in each solvent. This statement is also known as the Nernst distribution law. Mathematically, the ratio of solute in two immiscible solvents at equilibrium is written as the coefficient of distribution K, in which K is equal to C1 over C2, where C1 denotes the concentration of solute in solvent 1 and C2 denotes the concentration of solute in solvent 2. However, the value of K will only be constant as long as the molecular weight of the solute across the two solvents are the same, i.e., there are no association or dissociation taking place. So what is association and dissociation? Association is a process of aggregation of atoms or molecules into larger units held by forces weaker than chemical bonds, such as the association of acetic acid in ether. Dissociation is the reverse process of association, in which dissociation is a process of dividing molecules to form smaller ones, such as the dissociation of acetic acid into the ions. If there happens to be an association or a dissociation process involved, such as in the following reaction, then the equilibrium constant would become as follows. After some algebraic manipulation, we will get a linear regression equation log C organic is equal to n log C water plus log n over K. Plotting log C organic versus log C water will yield a straight line with the slope of n and the intercept of log n over K. Here n denotes the degree of dissociation while K denotes the equilibrium constant.
The equipment used in this practicum consists of a burette, a lap stem, a separatory funnel, and a Erlenmeyer flask. For the materials, we use acetic acid with normality of 1, ether, sodium hydroxide solution with a normality of 0.2, aqua test, and also oxalic acid for the detergent process. The procedure for this practicum consists of two main processes. First is the standardization of sodium hydroxide solution, and the second is determining the distribution of acetic acid into immiscible solvents. First, we take 10 milliliters of oxalic acid with normality of 0.2 and put it inside an Erlenmeyer flask. Next, we titrate the acid solution with sodium hydroxide 3 times, while noting the required volume of its titration. The second process is determining the distribution of acetic acid into immiscible solvents. First, we make solution of acetic acid of various concentration, ranging from 0.04 to 0.2 normality, and put 15 milliliters of its concentration in a separatory funnel. Then we add 15 milliliters of ether to the separatory funnel and shake the mixture until the mixture is separated and in equilibrium. Finally, we take the water-rich layer and titrate the solution with standardized sodium hydroxide solution to determine the equilibrium constant and the dissociation degree.
Here are the data gathered, and from the calculation of titration, the normality of sodium hydroxide solution is found to be as follows. Here are the actual concentration of acetic acid in water before and after the addition of ether, measured by titration. After all the concentrations are known, the logarithm of seawater and sea organics are taken and plotted to yield a straight line with the slope of 1.1122 and the intercept of minus 0.2246. Slope represents the degree of dissociation, while from the intercept we can find the equilibrium constant to be 1.86545. Next up is the discussion. An extraction process is done to determine the distribution of acetic acid across water and ether. The extraction is done using a separatory funnel by shaking and opening the valve to dispose of the vapor buildup caused by the volatile ether. Initial concentration of acetic acid solutions are measured by 3 times titration with sodium hydroxide solution and found to be as follows. After the extraction, the mixture will separate into 2 layers, with the upper layer containing the acetic acid and ether, and the lower layer containing the acetic acid and water. The water layer is poured into an Armayer flask and added into it a few drops of phenolphthalein, and then titrated with sodium hydroxide to determine the concentration of acetic acid in water and thus in the ether. The concentration in water can be found by the titration equation, while the concentration in the ether can be found by subtracting the initial concentration and the concentration in water. The plotting of log sea organic versus log seawater will yield a straight line with the equation as follows, with the coefficient of determination value to be 0.9436. The KNN value is then found to be 1.86545 and 1.1122 respectively. From the results, it is clear that after the extraction, the concentration of acetic acid is greater in water than in ether. This means that acetic acid has more affinity to water than ether. This is because acetic acid and water are both classified as polar protic compound, while ether is classified as a non-polar compound. This result goes along with the calculated value of K of 1.86545. Because the K value is the ratio of concentration in water and ether, a K value greater than 1 means that the concentration of acetic acid in water is greater than the concentration of acetic acid in the ether. The N value of 1.1122 indicates that there is indeed an association or dissociation process occurring in the mixture, with the association happening in the ether and the dissociation happening in water, and the reaction as follows.
From this experiment, we can conclude that, first, the equilibrium constant value of acetic acid in water and ether is found to be 1.86545, which implies that acetic acid has more affinity and more distributed in water than in ether. The second is the degree of dissociation is found to be 1.1122. As expected, there would be an association or dissociation in the mixture. And that's all for our presentation. Thank you for watching.